Hello, Assalamualaikum and Salam Sejahtera. This is the recorded lecture for Chapter 4 Diffusion, or based on the outline of the course, which is Section 5.1. Now, before we begin, I would like to stress that it is important for you to read the book, this chapter in particular, and try to understand as much as possible because the presentation that we're going to do today, based on the slides, are not very comprehensive. Okay, so make sure that you read the whole chapter on your own, and then hopefully with this recorded lecture, I would like to stress a few things and help you to understand some of the important concepts that you need to know. Now, if you remember correctly, right, in chapter 3, we have done thermal oxidation. Now, thermal oxidation, the process involves heating up silicon wafer inside oxygen environment at very high temperature. And what will happen is that the oxygen will react with the silicon, producing silicon oxide on the surface of the wafer. Now, diffusion in essence is the same thing, whereby you have your wafer, okay, and then you heat it up at very high temperature, ranging between 900 to in the excess of 1200 degrees Celsius, with the addition of a thin layer of impurity atoms on top of your wafer. What will happen is that these impurity atoms will start to diffuse into the wafer. So you can imagine that the wafer is absorbing these impurity atoms. Now, this happens based on three mechanisms, right? So which is what we're gonna look at in this particular slide, which is impurity diffusion. So let's say this is your wafer, okay, and then what you do is that you deposit a thin layer of impurity atoms, which are your dopants, and then you heat it up at very high temperature. So once you heat it up, the atoms will basically be relaxed and moving around, vibrating, and it will absorb the impurity atoms to diffuse inside. So the absorption of impurity atoms into your wafer is the process of diffusion. And then this can happen based on either substitutional or interstitial. Okay, interstitial. Now remember the concept of point defect. Remember, a point defect is a defect in the lattice structure of your crystal of one particular lattice site. So this one in in uh in diffusion, right? So diffusion can happen based on substitutional. So if you look closely here, okay, if you look closely here, the substitution can happen when you have a vacancy. So a vacancy is when a lattice site which is supposed to be occupied by silicon atom, but the silicon atom is missing. It's gone somewhere. We don't know where it's gone. So you have a point vacancy. So what can happen if you have an impurity atom, and when diffusion happens, so that impurity atoms can reside in that vacancy spot. Okay, so once it is residing inside a lattice point, therefore covalent bonding will happen between adjacent atoms, and therefore you can have sharing of electrons or holes. So you can contribute in terms of extra electrons or extra holes. So that is one way of substitution. So you have substitution by vacancy, and then you can have another type of substitution whereby you have an impurity atom, okay, impurity atom pushing away an existing silicon atom which resides in the lattice point. So what will happen is that the impurity atom will push away the silicon atom out from this lattice point, and then the silicon atom will reside in an interstitial position, okay, and then this impurity atom will then be substituted into the lattice point. The silicon atoms which has been substituted will basically just reside in the interstitial position. Interstitial position, if you can recall, is when you have the atom residing in an area or volume which is not the designated lattice point according to the crystal structure. So it can be in between all the other atoms, like like so. Okay, or you can have, so that is, so these two, so these two are substitution. All right, so substitution is when your impurity atoms reside in the lattice point and therefore can contribute to the additional holes or electrons to the wafer. Okay, so that is substitutional. And you can have another mechanism which is interstitial. Interstitial is basically when you have your impurity atom. During diffusion, it will be absorbed by the wafer and it will reside in an area or volume in between the silicon atoms. So it will not be located in the lattice side, but somewhere in between. So it can basically just move around somewhere in between. So it depends on where it wants to move, right? So this is what we call interstitial diffusion. So this is interstitial diffusion. This is substitutional. Okay, this is also substitutional, but this is substitutional plus interstitial C mechanism. Okay, so substitutional, that means the impurity atoms reside in the lattice point. Interstitial diffusion, the impurity atoms reside in the interstitial position, which is which it will not be involved in covalent bonding and contribution to extra electrons or holes. So it resides somewhere in between. So what we want really is substitutional. Why? Okay, first of all, because substitutional is the only diffusion mechanism whereby you can have the impurity atoms in the lattice point, therefore forming covalent bonding with the neighboring atoms and contribute with the extra holes or electron. And these extra holes or electrons can be used to change the conductivity of the silicon atoms, or sorry, of the semiconductor, and therefore it will become electronically active. Okay, diffusion by interstitial on the other hand, okay, there's no covalent bonding, so there's no way for the extra holes or electrons from the impurity atoms to be transferred into the wafer, and therefore it cannot be included in the electronic properties of the material. Okay, so that's the first reason. The second reason is that the interstitial diffusion is fast. So this is fast diffusion. Why is it faster? Because it has a higher diffusion coefficient D. And the drawback of that is that it's hard to control. Hard to control. When you do diffusion, you are not only controlling how much impurity atoms that you put into your wafer or you diffuse inside your wafer, but you want to control the profile or the shape of your diffused volume or region. Okay, because the size and the shape will determine how your device work. So moving on, so once we understand the impurity diffusion mechanisms, okay, either substitutional or interstitial, we can look at the mathematical representation of this diffusion process based on, yeah, so we want to look at the mathematical representation of this diffusion process. Now we have looked at the fixed first law. This is diffusion when you have thermal oxidation. So thermal oxidation is based on fixed first law, whereby particle flux J is proportional to the negative of the gradient of the particle concentration. Okay, and D, capital D, is diffusion coefficient. Now J is your particle flux. Now if you use continuity equation for particle flux, you can get the rate of increase of concentration is equal to the negative of the divergence of the particle flux. So you get this equation here. This equation here in one dimension. So with this, you can get what we call the second law of diffusion, whereby you combine the first law and the continuity equation to produce this fixed second law of diffusion. So diffusion will follow the fixed second law of diffusion rather than the first one. Here, one thing that you need to take note is that D, diffusion coefficient, is assumed to be independent of concentration. What does it mean? It means as the diffusion process occur, D will be constant and it will determine by the equation. Okay, D naught exponential EA over KKKT, which we will see later on. So D does not change, regardless of how much concentration of impurity atoms there is within that volume of wafer or silicon bulk volume. Okay, so D is assumed to be independent of concentration of what? Of impurity. So it's the same throughout the wafer and throughout the process of diffusion. All right. So when we have the fixed second law of diffusion, diffusion can happen based on two ways. Okay, two ways or two models. Right. The first model is called the constant source diffusion. Okay, so this model, we get this model based on how we do the partial differential equation of 4.3. So based on the partial differential equation to solve this fixed second law of diffusion, we can have two different models for diffusion. Now the first model here is constant source diffusion. So how do we get, so the most important thing is that this equation here. So this is the equation that governs the N, capital N, which is the concentration of impurity as a function of X, X being the distance from the surface. Remember, if you want to read this graph here, you imagine that you have your wafer and then you deposit some impurity on top, and then you carry out the diffusion, so the atoms will be diffused inside, right? So and then what you do is you turn it 90 degrees. So here is the surface where you have deposited the impurity atoms, and then the diffusion will happen downwards like this. So the y-axis here is your concentration of impurity at the surface and along the depth of your junction, or the profile of your diffusion. Okay, and then x here is the distance or the depth. All right, so it's the depth actually. Okay, so let's clear that one again. Now this is the equation, right? So this equation governs these graphs here. So how do we get this equation? Is by doing so it is not shown here, but if you do partial differential equation, you can solve this the equation before this one. You can solve this equation and get the first one here. So n as a function of x and t is equals to n naught. So what is n naught? N naught is the concentration at the surface. So the concentration of impurity at the surface of your wafer. And then you have this function here. This function here is called the ERFC, or the it's the complementary error function. Okay, complementary. Oh yeah, this one. So here, complementary error function. So what is complementary error function? Is basically, if I were to just fast forward a little bit. So ERFC is a function. Okay, it's an equation or a function similar to Gaussian equation. So this one is a Gaussian equation. So Gaussian equation is this line here. So complementary error function is something like Gaussian function, but it drops out faster than Gaussian function. So it's a type of function. It's an equation to describe a line on your graph. Okay, so the function of the line is complementary error function, which is very similar to Gaussian function. Similar to how you can have normal distribution, Gaussian distribution, you can also have complementary error function distribution. Now, reverse back to the constant source diffusion. So this is the equation that governs the line. Okay, the line here. So this equation describes all these lines. Okay, this equation here. And then you can have an equation to calculate the dose. But before we go there, okay, let's look at the equation that describes the line first. So as you can see from this graph, you have 3, right? 3. Now, don't worry about the 3. don't worry about the tree. Let's look at the number one first. Okay, so number one is after doing the diffusion at a certain time, right? So diffusion, recall again, diffusion is heating up your wafer. Before that, you deposit a thin layer of impurity atoms. So how can you deposit? You can use CVD in vapor form. So in vapor form, you can actually form a thin layer on your surface, and then it forms a thin layer. Or you can use sputtering, or you can use any other deposition method, as long as you can have a desired concentration of impurity atoms on the surface of your wafer. And then you put it inside a controlled chamber. You heat it up from 900 to more than 1200 degrees Celsius. And then what will happen? The impurity atoms at the surface will start to be diffused or absorbed into your wafer. So let's say after 1 hour, okay, this is the profile. Okay, at time, okay, at time equals to zero, you can say that all the impurities are here, right? It's on the surface. After 1 hour, then you can, some of them will diffuse. So it will diffuse to this. So that means all this area of volume is full or occupied by the diffused impurity atoms. All right. Okay, so while you are doing the diffusion, you keep on maintaining the concentration of impurity atoms on the surface to be N naught. So that is why we call it constant source diffusion. So while the diffusion is happening, you keep on adding more and more impurity atoms on the surface to maintain N naught to be constant. Okay, so as some of the atoms move or diffuse into the material, more is added to maintain and not to be constant. That is what it means. And then as you increase the time of diffusion to 2 hours, then more and more atoms will start to, impurity atoms start to diffuse deeper inside. Okay, it will diffuse deeper inside. Okay, the deeper you go, okay, so let's say this is your junction, right? So this is the junction. So the deeper you go, the lower the impurity atom concentration, because now if you are here, if you look at this particular depth, okay, so if your depth here is nxn, so the concentration of impurity atoms here is equivalent to this point here. So near the surface is n naught, so down here is n something, and let's say n, because here is nxn. All right, similarly, if you are looking at this point, then the impurity atom concentration is there. Okay, so if you know the concentration of atoms, impurity atoms within a volume, you can find therefore the total dose or the total impurity atoms which has been diffused into your material, and that is given by this equation here, which is just the integration of this equation. So when you integrate the equation, let's say after 1 hour, this is your profile. So the total dose is essentially just the area under this curve. And similarly, if you increase the diffusion time to 2 hours, then this is the total area. And furthermore, 3 hours, then this is the total area, and so on. Okay, so N naught is the surface concentration, and you make this constant. Hence, the name constant source diffusion. Now, what is NB? NB here is your background uh, doping concentration. Okay, remember when we fabricate devices, that silicon wafer, that silicon wafer must already have been doped with a uniform doping concentration. Okay, if you use pure silicon, it's useless. So we use diffusion to create a shallow junction or an area which has the opposite doping type than the background doping of the wafer. For example, right, let's say you have a wafer, and then your wafer is already n-type silicon, right? it's already doped during the synthesis process with some impurity to make it n-type. What you want is you want to create a shallow junction like this, which is p-type, p-type silicon. Okay, so this is when you have to cover this portion with a mask or your barrier layer, and then you deposit on the surface your p-type dopant, and then you carry out the diffusion so that the dopant atoms will diffuse into forming the shallow junction within the n-type silicon wafer and leaving behind a shallow junction, right? So NB is the doping concentration of the original wafer. So if it's n-type wafer, then NB is this. So that's why it's and it's uniform throughout the wafer. Okay, it's uniform throughout the wafer. And then if you have a so if you see that your diffusion looks like this, okay, that means here is anywhere around here is the concentration of impurity atoms is Mb, and the impurity atoms is the N dopant, and inside here it's NXT with the surface to be N naught. Okay, and this one is represented by this graph here. Okay, so that's why you have NB here to be a straight line, because throughout the wafer it's already uniform. The background doping of the wafer N type is already uniform, so it's a straight line. Okay, and then another thing that we need to take note when we are doing diffusion is the concept, or this not concept but the figure of dt. What is dt? Dt is the time, diffusion time, times the diffusion coefficient. Okay, so therefore we can say that the dt product of diffusion 3, diffusion 2, diffusion 1 is different because D3 is carried out at a longer time, 3 hours. This one is 2 hours, this one is 1 hour. Okay, and then this is complementary error function, which is given by this. So if you want to look into it, so you have to play around with your calculator or look inside maths book. Okay, so clear constant source diffusion. Now, this is very important. Okay, the concept to understand what is a constant source diffusion is very important, and to understand which equation governs it to describe this line. Most of the calculation involved in this chapter is basically understanding this, understanding the concept of constant source, and then knowing which equation to use and how to use it. Okay, and then the next one, the second model for diffusion is limited source diffusion. The difference between this and the constant source diffusion is, of course, the what, the concentration of impurity atoms at the surface. Okay, if previously we always maintain the concentration of impurity atoms to be N naught, here we do not maintain it. What we do on the other hand, we set a particular concentration. Let's say before we do the diffusion, we deposit our impurity atoms on the surface with the impurity atoms of N naught 1. Okay, and then we stop. We put it inside the diffusion machine, and diffusion machine is basically just heating it up. So we heat it up. Some of the impurity atoms on the surface will be starting to diffuse into your silicon wafer. So as it diffuses inside, okay, some atoms will definitely basically reside in this region here. So what will happen to the impurity atoms on the surface? The concentration will be reduced. Why? Because some of them have already been diffused into the material, so less and less impurity atoms will exist on the surface because some of them has already been diffused. So that is why as you keep on in, so after 1 hour, okay, you can see this is the profile. After 2 hours, you can see that now most of the atoms have diffused, the impurity atoms have diffused in this region, and the concentration of impurity atoms on the surface of the wafer also drops. Again, it drops because some of the impurity atoms have been diffused and it is not being replenished by additional impurity atoms, because you just already set the amount to be a specific amount, which is Q, which is your dose. So initial impulse with a dose Q. So you have a particular dose, you deposit a specific amount of impurity atoms, and then you don't add any more. You put it inside the oven, you carry out the diffusion process. Therefore, as the diffusion process carries on, longer and longer, less and less, more and more atoms, impurity atoms will be diffused deeper inside your wafer. It goes deeper, especially in after 3 hours, and at the same time less and less impurity atom concentration is on the surface. Okay, and then this line here is represented by this equation. So this is the equation that represent this line. It's a Gaussian equation. Okay, in contrast to this one is complementary error function. This one is a Gaussian equation. So this equation describes the Gaussian distribution of limited source diffusion. Okay, and n naught is the surface concentration. Okay, and n, since it is a limited source diffusion, so n naught is equals to q over root square of pi dt. Okay, so as you can see here, as you increase the time t, dt product will be bigger as the denominator is bigger than the division here is smaller. So n naught will become smaller and smaller as you carry out the division longer time. Okay, so I hope that is clear. And these two are the most important thing that you need to understand: constant source diffusion, limited source diffusion. So this is the comparison between constant source and limited source. So constant source, the mathematical model is based on complementary error function. Limited source is based on Gaussian distribution. They are essentially looking like the same kind of curve, except that for complementary error function, it drops down faster compared to Gaussian equation. Okay, so now that we have looked at the mathematical model of two different types of diffusion model, constant source and limited source, the diffusion coefficient itself, D value, depends on what type of diffusion are we doing, whether we are doing substitutional diffusion or interstitial. Remember that we always prefer substitutional. Why? Because the substitutional involve covalent bonding between impurity atom and the silicon atom. Therefore, you can contribute extra electrons or holes, and then it is slower and easier to control. Whereas interstitial diffusion, the impurity atoms reside in the interstitial location, and then no covalent bonding, no sharing of electrons or holes, and at the same time, the diffusion is very fast and hard to control. It's very hard to control the dosage or the shape or the profile of your diffusion. So as you can see here, right? So you can see this graph here, graph A, are all the type of dopants that normally constitute substitutional diffusion inside silicon. Like for example, gallium, aluminium, indium, phosphorus, boron, arsenic. This one is what? SB is antimony. Okay, and then on the other hand, um, if you interstitial diffusion, elements such as lithium, copper, gold, and iron. So that's why you never hear people using iron, copper, gold as dopant. right? Because they never actually, they are smaller in size, therefore it will always um, experience interstitial diffusion. It will never actually experience substitution, right? So this type of diffusion process determines what D is. So as you can see here, right? Let's zoom in a little bit. Let's see if I can zoom in here, right? So as you can see, okay, this is a Arrhenius plot. Moving to the right is the decreasing in temperature, moving to the left is increasing temperature. So as you can see, the higher the temperature, the higher your diffusion coefficient. So you look at the value here. This is 10 to the minus 11. This is 10 to the minus 12. So 10 to the minus 11 is higher than 10 to the minus 12. So increasing the temperature will increase the diffusion coefficient. So as you can see, substitutional diffusion, the diffusion coefficient is reasonably quite low, 10 to the minus 11. In contrast, if you look at the interstitial diffusion, okay, the value is much higher, 10 to the minus 6 only. Right, so it is roughly around 4 to 5 order of magnitude higher. So, meaning to say it is, yeah, so 5, like much more faster, basically. Right? So yeah, 10 to the minus 6 compared to 10 to the minus 11 or 10 to the minus 10. So that's why substitutional diffusion is slower, much slower. Okay. So again, diffusion coefficient, how to calculate diffusion is based on this equation, and we assume D to be constant throughout the process. However, we shall see later that based on the concentration of impurity atoms, D might not be constant, or it's not really constant, and it's not suitable for us to assume that it is constant. So as long as the impurity concentration is well below the, or slightly below the intrinsic concentration of your wafer, then you can assume that D is constant, whereby D is equals to D naught, which is here, diffusion coefficient value, okay, times the activation energy over KT, Boltzmann constant, T absolute temperature. Remember to convert it to Kelvin. So this is an example of how to calculate it. Okay, very straightforward, something that you have done before. All right. Okay. So when we do diffusion, right, there's a situation where we call successive diffusion. Recall that diffusion is a process that happens at very high temperature. That's it. So the only thing that you need to do is make sure that you have impurity atoms and then you heat it up at the right temperature. As long as the temperature is high enough, diffusion can occur. Okay, diffusion can occur as long as you achieve the activation energy and the temperature is high enough that you can have a considerable value of diffusion coefficient. So as long as there's enough temperature, diffusion will occur. So successive diffusion is a situation whereby if you have done one diffusion, okay, you might have to do another diffusion for a different area in your on your wafer or different layer, right? So you have many junctions of different materials and different characteristics, so you have to repeat diffusion process for these different features on your integrated circuit. Now you have to do the diffusion process for the whole wafer. So let's say you have your whole wafer, right? So let's say this is your whole wafer. So you need to have one here and another one, a bigger one here, or maybe a smaller one like this. So you have N-type silicon, you have your P-type here, and this one is P-type, very high doping. This is N-type. So all this shallow junction, or we call it well, diffusion well, must be done in 3 different diffusion processes, right? So you have to deposit this one first, and then you diffuse, and then you deposit for this one, then you diffuse, and then you diffuse for the third one as well. So as you do it, the whole thing must be included in the process. So once you have done the first one, okay, then you carry on to do the second one. The first one here will also experience the high temperature. So when it experiences a considerably high temperature, further diffusion will happen to this shallow junction. So it goes down even deeper, and as it goes deeper, the concentration of the impurity atoms within the volume will drop as well, because it covers a higher or larger volume of area. You know what I mean? So if you have three successive diffusion processes for your device, that means each one of them will experience the diffusion process of the next cycle. So successive diffusion using different times and temperature, final result depends upon the total DT product. So when you design your fabrication process, you have to take this into account. What I mean by that is that, for example, let's use the same example, same structure. You first do this one, right? You first do this diffusion, and then followed by this diffusion, and then followed by this diffusion here, right? So 2 and 3. So in order to make sure that the profile here is accurate, for the first diffusion, you have to consider that you have to make the whole device go through the second and third diffusion as well. So you have to compensate by doing the diffusion at a shorter time, so that it covers a much shallower and smaller volume. And then as you go through the second cycle of diffusion, more diffusion will occur, so it will cover a larger volume. And then after the end of the third diffusion process, it covers the desired actual volume that you wanted to cover at the first place. Okay, so you have to take that into account. So all this, that means the DT product will keep on increasing, and then the DT product is the summation of all the diffusion processes the successive diffusion processes your single wafer will have to go through in order to produce your integrated circuit. Okay, now the next concept that you need to understand is diffusion solid solubility limit. Solid solubility limit is basically looking at the limit of which silicon can absorb absorb impurity atoms. There is a limit to the amount of given impurity that can be dissolved or absorbed by silicon, and we call this the solid solubility limit. And if you add additional impurity atoms to silicon beyond this the solid solubility limit, you will not change the electronic properties of the wafer anymore. There's no change in the conductivity and whatnot. So those extra impurity atoms basically is useless. Okay, it will not be electronically or electrically active. At high concentration, all of the impurity introduced into the silicon will not be electrically active. So it will not basically contribute extra electrons or holes to your wafer. Now this graph here shows you the line for solid solubility limit of different dopant. Okay. Now, like for the solid line is the solubility limit. So if you increase the impurity concentration beyond the solid line, that means it will not contribute to the enhancement of the electronic properties of the wafer. So you always target to do the doping or diffusion with impurity concentration below the line. Okay, so for example, if you look at a boron here, right? So boron has a solid line and then a dotted line. So a dotted line, on this dotted line, still the extra impurity concentration will contribute to the extra electrons or hole. But if you go to a higher temperature and higher concentration, it will no longer contribute. Okay, so you need to only use this impurity concentration for boron. For antimony, on the other hand, you can only use it around this region, this concentration. So too low also cannot, too high also cannot, but within this region. For arsenic and phosphorus, the whole line will basically can be used. Okay, the whole concentration from here to here can be used. Okay, and then if you increase the above this line, you cannot. Okay, above this line for arsenic and phosphorus, it will not be electrically active. So when you come across a question saying that you are doing diffusion at the solid solubility limit, what it refers to the value of N naught to be equal to anywhere on this line here, depending on what temperature that you use. So basically it refers to what is the N naught. Okay, and the N naught is at the solid solubility limit. Okay, now diffusion PN junction formation. Remember when I told you that when you do diffusion, right, you are doing it on a wafer which is already doped with something. So it can be N-type silicon or P-type silicon, right? And it has its uh, uniformly doped background impurity concentration. So NB is the background concentration. So that's how you can get this straight line here. So when you diffuse your another type, so if this is N-type, you diffuse P-type material here so that it will create this junction here. Okay, so which is this line. When you plot the graph, okay, what happens to this line here, whereby N naught is equals to NB. So when N naught is equals to NB, you have what you have is that you have the number of electrons is equals to the number of holes, right? So NP equals to NN. So when that happens, that means you have a neutral charge. Okay, because equal number of positive charge equals and equal number of negative charge is basically cancel out each other, so becomes neutral. So that's why effectively at this junction, at the depth, so at the depth here, you should expect it to have no extra electrons or holes, or basically charge neutrality. So anything below this neutral region is N-type, anything above is P-type. So that's why you can have this is your wafer region, this is your junction region or your well region, and in between is your PN junction. So in between this is your PN junction, right? So your PN junction is neutral. Okay, because the amount of electrons and holes are the same. So that's why effectively your net impurity concentration at the junction, PN junction, is equals to 0. Okay, so deeper than that, net impurity concentration is based on NB. Shallower than that, it depends on this line. Okay, I hope that is clear. All right. So when we dope a material by diffusion, we know that what we do is we are contributing extra electrons or holes, which are basically charge carriers. And effectively, when we doped, we change the electronic properties, in particular the conductivity. Okay, and conductivity is basically just the reciprocal of resistivity. So your material, if you dope your wafer with certain amount or certain dose of dopant, the resistivity will change. And this graph shows you how the impurity concentration will actually change the resistivity. For example, this is for you to find NB. Remember when I told you that uh, before doing the diffusion, your wafer is already doped with a uniform background doping, right? Either it is N-type or P-type, NB. So NB here depends on what is the impurity concentration of that background. Okay, so NB here can be NA or ND. NA is acceptor concentration, ND is donor concentration. By knowing NB, we can use this graph to find out what is the corresponding resistivity of your wafer. Okay, so this makes our life easier so that we don't have to calculate, because in reality we have to calculate like this, right, based on this this equation for n-type. So if your wafer is already doped n-type, so you follow this line, and then all you need to know is the impurity concentration is Nb. So if your Nb is here, okay, if your Nb is 3 to the power of 10 to 16, then therefore you know that the resistivity of your wafer should be around this value here, 10 to the minus 1 ohms cm. Okay, so you can use this graph to find Nb and to find the resistivity of your wafer. Sometimes the question will give you the resistivity and then you have to find out what is the Nb. So it's vice versa. Okay. Right. So we have looked at go back to the beginning. Just now we looked at two types of diffusion model: constant source diffusion and limited source diffusion. Similar to thermal oxidation, whereby you have dry oxidation and wet oxidation, whereby in order to produce a thick and high quality thermal oxide, you combine the two processes, right? Similarly, here also we can combine the two processes in what we call the two-step diffusion. So the first step is you do constant source diffusion until you get the right dosage, and then you cut off the supply of your impurity atom. And then the second step is the drive in step, whereby you want to drive in the impurity into your wafer, okay, based on limited source diffusion. So if you look at this graph here, okay, the first line here is an impulse. That means you deposit a very thin impurity layer on the surface, and then you carry out a very short time of constant source diffusion, okay, until you get your desired dosage, and then you stop the supply, and then you carry out a second diffusion process to drive in, with what we call the drive in. So the first step is the pre-deposition. The second step is the drive in. So the drive in is when you use the total dosage to drive it inside to create your desired profile of your well. Okay, and as you know, with the limited source diffusion, the surface concentration of impurity atoms will drop as the time goes in, as you drive in. So the first impulse is based on complementary error function Then the second one is based on Gaussian distribution. The first step to establish the dosage. The second step is to drive in so that you can get the correct shape of well. So this is the example calculation. Okay, I want you to look at this very carefully. So in this particular example, a boron diffusion is used to form the base region of an NPN transistor in a 0.18 ohm cm n-type silicon wafer. So here it is given to you the resistivity. Therefore, you need to find the Nb. How do you find the Nb? Again, you can use this graph here. The Nb or Nd rather, because we know that it is n-type, so we know it is a donor. So the Nb is equals to Nd, which is 3 times 10 to the minus 16. Okay, and then we can use that for our equation. So the first step is a solid solubility limited boron. So here, solid solubility limited boron. So here you can know what is your N naught. Okay, what is your N naught? Is a solid solubility boron pre-deposition performed at 900 degrees for 15 minutes, followed by the second diffusion for 5 hours at 1100 degrees Celsius. So the question asks for find the surface concentration and junction depth. So you need to find N naught and the Xg for after step 1 and after step 2, after the drive-in. Right, and not an Xg. So let's do the first one. The first step, pre-deposition step, solid solubility limited. So we know that it is boron, 900 degrees. So the solid solubility limit for that is around this region here, which is your N naught. So your N naught is approximately 1.1 times 10 to the minus times 10 to the 20 power 20. So this is your N naught. So you get this N naught from the graph. Okay, and then you calculate your D. So you know what your you know the equation for D. You plug in the value for D naught. 10.5 is for boron. Okay, and then 3.69 is the activation energy. The temperature here, don't forget to convert it to Kelvin. And this is Planck's constant. You get your D. So this is your D. D is constant. T is given to you 50 minutes, which is 9,000 seconds. You can convert it to second if you want. And therefore, your DT product is this. Okay, why do we convert this to second? Because our diffusion is in second as well. Okay, because we use 10 to the 10.5 D naught is second. All right, so we use second. Okay, so you get that, you get dt 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 product. Okay, and then you go back to the equation that governs the constant source diffusion. So go back for us to see what it looks like. This one. Okay, so 2 times, so n naught ERFC x, which is your junction depth, 2 times the root of dt. So go back. So this t, 2 times root of dt is this value here. We want to find x. We know what is our n naught, okay, which is this one, right? And then we can also find, so this is our first equation. We already first get our first equation. And then we can know our dose. Okay, our dose is according to this equation as shown in the previous slide, in this slide, this one. Okay, for constant source. So remember, for dose, for constant source and limited source are different. Okay, okay, and then we do for the second, the drive in, change the temperature, do the same thing. All right, find the diffusion coefficient and then plug it inside this equation for Gaussian distribution of limited source diffusion. Okay, so this is your n naught. This is your n naught for number 2, n naught 2. All right, so how do we get this? This is from here. So based on equation 1, so this is equation 1, you can get the junction after the step is this one. Junction after the first step is this one, and junction after the second step is this one. So this is xj1, xj2, and then just now n naught 1 is equals to this one. So n naught 1 is this one. Okay, n naught 2 is this one. Okay, how do we do it? Because we calculate it using this one. Right, so straightforward. So when we do when we do diffusion, right, the diffusion is not only happening downwards, but it's also happening laterally. So diffusion is really a 3D process. As impurities diffuse vertically, they also diffuse horizontally in both directions. Diffusion proceeds laterally under the edge of the mask opening. So when you are designing your process, you need to take this into consideration. So if you don't want the lateral diffusion to be too large, that means your deposition step, your pre-dep step, when you are depositing the impurity atom, must be in a smaller area compared to the NA area which you desire. All right, something like this. Now, so remember when I told you just now, diffusion coefficient D is constant, right? But it is constant only when n naught is lower or comparable to Ni, which is the intrinsic concentration of carrier. Okay, if it's above that, if your impurity concentration is higher, then your D value will have a function of x, so it will not be a constant anymore, depending on what type of dopant it is. So it will follow either one of these equation, A, B, and C. So this is the standard one. This is the standard one. Okay. If the impurity concentration is low, then it will follow this one. It's constant. If not, then it is according to these two equations. So it depends on the impurity concentration at that particular depth. All right. So this is good in order for us to produce a very abrupt high concentration. So high concentration and abrupt. So if you look at this one, right, you gradually drop, right, the concentration. Yang on the other hand, if you have this one, that means you abruptly change it and then it becomes constant at that particular at your junction here. So you have shallow, high concentration, shallow junction. All right. Sometimes if you use phosphorus, okay, diffusion profile for constant source diffusion at 950 degrees, it is abrupt and then it has a kink. So this is the kink, and sometimes this is not very desirable. Okay. Okay, so we have finished with diffusion. We have finished with diffusion, and then the rest of the chapter is looking inside sheet resistance. I think this is very straightforward. Okay, you know what sheet resistance is. If you do not know, then you have to read it up again. Basically, this is the equation that describe resistance. If you have a material like this, okay, resistance is basically the rho, which is resistivity times length over A. So the larger the area, so cross-sectional area, the lower is the resistance, and vice versa. And resistivity is basically just the inverse or the reciprocal of conductivity, and conductivity is given by this equation here. And if we rearrange this equation whereby we separate W and T for A, so A is basically the width times T the thickness or the height. Okay, so we separate the two, we get this one whereby RS is equals to conductivity over thickness. So we get sheet resistance. So sometimes you need to know your sheet resistance. This is how you get it. Okay. Now, if you look at the IC design, okay, you will find out that they for metallization, when you put in the metallization, the track for connecting between different parts of the circuits, okay, they have a standard size and dimension, and this is done to control the total resistance of the whole circuit. So you want to know the resistance of the whole circuit, because at high frequency and at very low current, this kind of values will actually determine the performance of your device. Now looking at these two different shape of resistor, okay, they actually have the same R. Resistance are the same. Okay, how can it be the same? Because you know the resistivity. Okay, so the resistivity does not change. So if it's the same material, then the resistivity should not change. So what you do, you change the dimension in order to get the same R value. So as you can see, you can have different sizes but the same R value. Okay, so one square is equivalent to so this square and this square will have the same resistance. All right. And then the end part will have its own contribution as well. In this particular example, one contact here is equivalent to 0.65 square. If your end contact is like this, it's 0.14, and if it's like this, then it is 0.35. Effective square contributions of various resistor end and corner configuration. If you have a corner like this, if you have a corner like that, that means this particular square contributes to only half square. Okay, so depending on your resistivity, one square will contribute to a specific value of R. So if you have the same amount of square, regardless of the size, if it's the same square, then the value of total R is the same. So the total for each, the big one and the small one, is 8.3, because you have 7 square in the middle, and then the ends will contribute another 1.3 square. Well, I guess that's all the important things that you need to know. The rest you can just read through and understand. For example, 4-point probe and all that are very quite straightforward for you to understand. Okay, so these are the method we use to okay, the first one, okay, the 4-point probe is to measure the actual sheet resistance. Okay, we can estimate the sheet resistance, right? But how do we actually measure it? By using 4-point probe. Okay, and then another method is by using 4-point but in a different configuration, which is van der Plas method. So in both methods, it's important to know the dimension of certain things, like for example, the distance between the probes and so on. And this one is the distance between the points. Okay, so this one is a method. Groove and stain method is the method to measure the actual junction depth measurement. So when you do diffusion, right, using the mathematical model, either constant source diffusion or limited source diffusion, you can estimate two things, right? You can estimate the concentration of impurity atoms at particular point, and you can know what is the junction depth. But how accurate is this? Okay, because it's just a mathematical representation. When you do the actual process, there's a lot of other external factors that you have to take into account, and sometimes these values will change, like the depth and so on. So when you do diffusion, you always have to do some test runs and do an actual empirical analysis, one of which you want to measure the actual junction depth, right? So if you want to actually calculate, or not calculate, but measure the junction depth, one method is groove and stain method. Okay, another one is angle lab technique. So if you want to know more, then you can read through. Okay, and then as you do it, okay, you can profile, you can plot this graph, carrier concentration versus depth. Okay, so as you can see, this is the actual graph. So remember, the mathematical model produce this graph, right? Where is it? This two graph lah, basically. Yeah, this graph, right? But if you do the actual measurement of impurity atoms at a particular point, then you get the approximate or the actual empirical data. Okay, and then you can compare between the measured one and the calculated one. Okay, so you can read through the process, the actual process that's happening, chemical process, but this one is not so important, right? But if you want to know, you can read through, including gathering. Why do we have gathering? So I want you to read through what is gathering, but essentially what it is, if you have a wafer, what you do is you introduce impurity, either impurity at the bottom or physical defect at the bottom, whereby so that it will attract, as you heat it up during diffusion, it will attract impurities which are not supposed to be there, such as heavy metals, some other metals, and so on. So you can have surface damage, or you can include impurity atoms at the bottom of the wafer as a trapping agent to trap all the other unwanted impurity atoms, which is not part of your dopants. Okay, so that's all. End of chapter 4. Okay, and if you have any question, you do ask me. If you can email me or ask through, you can follow. Okay, thank you.